Okay, welcome everybody to exercise 3 on page 116 of the workbook. Okay, and this is the first example that we're being asked to do where we're trying to calculate a line integral in 3 dimensions using this new method that we have. Okay, so let's read this problem together here. So they're giving us a vector field, okay, 3 components since we're in 3 dimensions here. And they're giving us a path that's kind of complicated. So C1 is a path that goes from 0, 0 to 1, 1 on 3 separate line segments. Okay, so we kind of first go up along the z-axis, then we move over a little bit, and then finally we come to 1, 1. Okay, so my first comment here is this would be a very difficult problem to do using brute force if we wanted to do this by parametrizing the curve. Okay, like you did back in sections 18.1 and 18.2, we would actually need 3 separate integrals, one for each piece of this curve. Okay, and that could be a lot of work. Okay, so what we're hoping when we do this question is that we can use the fundamental theorem of line integrals, because if we can, all that really matters is our starting point and our ending point. Totally doesn't matter how complicated the path is. Okay, to do that though, we need to first know or confirm that this is a conservative vector field. Okay, so in this case, we've got 3 components, which we're going to call F1, F2, and F3. And we're going to need to use the curl test in 3 dimensions for the first time. Okay, so curl test. And you can look back on page 111 and see that there was that big, long formula for curl. That's the one that we're going to need to use this time, since we're in 3 dimensions. The curl of f looked like this, and I'm going to start by just writing that formula out term by term here. So partial f3 partial, y. Okay, and just to remark that you could use a determinant to do this if you wanted to. I'm just going to write the formula down as I see it from page 111. There I go again, sorry. Okay, that should be with respect to y. All right, so partial f3 partial y minus partial f2 partial z I. Okay, then we had a plus partial f1 partial z minus partial f3 partial x. Okay, this is a lot of writing. Okay, and then finally the third term looked like partial f2 partial x minus partial f1 partial y. All of that was our formula for the curl. Okay, let me just take a second to confirm that I wrote all of that down right. Okay, looks good. And now we need to actually calculate those partial derivatives, and what we're hoping is that everything is going to cancel out and we're going to get 0 for the curl, because that will tell us that this is a conservative vector field. Okay, so starting with f3, we need to take the derivative of that with respect to y, it looks like. Okay, so y is our variable, everything else is constant. If we do that, the derivative of x squared y is going to be just x squared. Okay, and then the derivative of y e to the z with respect to y is e to the z. Okay, so those two terms together are the partial f3 partial y. Then we move on to partial f2 partial z. Okay, so we're looking over at the f2 component and taking its derivative with respect to z. So let's see. Derivative of x squared z is just going to be x squared. Okay, and the derivative of e to the z with respect to z is still e to the z. Okay, and notice that this is looking good so far. Okay, if you subtract those two things, you're going to get 0. We'd like to get a bunch of zeros here. Okay, moving on. Next thing we come to is partial f1 partial z. Okay, so we're looking over here at f1, and its derivative with respect to z would just be 2xy. Okay, minus, now we move on to partial f3 partial x. That's going to give us a 2xy, and notice that those other two terms are going to go to 0. Okay, and again, those subtract to 0. I'm getting pretty excited here. And finally, we move on to partial f2 partial x. Okay, that's looking at this term again. And we take that derivative, we're going to get a 2xz, and the e to the z is going to go away, minus, ready for partial f1 partial y, that's going to give us 2xz again. And notice that sure enough, exactly what we wanted to happen happens here. We get zeros in all of those components, meaning that our curl vector is 0. And since that's 0, we know that f is a conservative vector field. Okay, f is conservative. Okay, so first hurdle is cleared here. We know that this is conservative, so we can use the fundamental theorem of line integrals. Okay, what's the next step here if we want to do that? Well, we need a potential function in order to use this method. Okay, I'm sorry, but we're going to need to do a little scrolling up and down. This is kind of a long problem. Okay, so remember what a potential function is about. Okay, it's about finding a scalar function that matches our vector field. Okay, in other words, what we want here is for our three components to be partial derivatives of some function that we're looking for. Okay, fx, fy, and fz, that's our starting point. Okay, so when we go down below, I'm just going to write down what you see at the top of the screen, what fx, fy, and fz are equal to. Okay, so fx was equal to the first component, 2xyz. Fy was equal to the second component, x squared z plus e to the z. Okay, and then finally fz was our third component of our vector field, which looked like x squared y plus y e to the z plus 1. Okay, and we need to take those things one at a time and see if we can figure out the function f that goes with, that produce those derivatives. Okay, so to get f of x, y, z, we need to integrate 2xyz with respect to x, okay, which means that x is going to be our variable and y and z are going to be constants. If you think about that, that means that the 2x that you see is going to integrate to x squared, and the y and the z are just going to come along for the ride. Okay, so our antiderivative looks like x squared yz plus a constant. Okay, but what is our constant going to look like in this context? Well, if x is our only variable, then y and z are being treated as constants, so this constant that we add may very well have y's and z's in it. Okay, so we need to think of our constant as being a function of y and z. Okay, and moving on to the second calculation. Okay, we're going to integrate x squared z plus e to the z with respect to y. Okay, notice that there are no y's in that entire formula, so when we integrate x squared z, we're just going to get x squared z times y, and same thing for e to the z, we're going to get e to the z times y, plus a constant, which this time may very well include x's and z's, because y is our variable this time. Okay, and then finally, we're going to integrate our third component with respect to z. Okay, so we're treating x's and y's as constants, so if we integrate x squared y, we're going to get x squared yz. Okay, if we integrate the second term here, the y e to the z, y is a constant. If we integrate e to the z, it's going to stay e to the z, so that term stays the same. Okay, and then finally, we need to integrate 1 with respect to z, so that's going to give us a z. And again, there's a constant, because this is an indefinite integral, and the constant may very well include x's and y's this time. Okay, so the observation is that all of these things need to be equal. And so the question that we're trying to answer is, what would these three constants have to be so that all three of these formulas match each other? Okay, let's start with the first equation up here. So P of yz, we need to go searching for things down below that we don't see in the first line. Okay, and I actually notice a couple of things. Okay, so there's an e to the zy that we need, that we don't have in the first line. Okay, and then down, okay, here, y e to the z, that's the same term, okay, that we have up here, so we've already taken care of that. We don't need it again. Okay, and there's also a z that we don't have, so we'll add that to our p of yz. Okay, that kind of takes care of the first line. And moving on to the second line, what would q of xz need to be? What's missing there? Okay, well, I think the only thing that's missing there is this plus z that's down here. So we'll make that equal to z. And remember, the goal here is to make all three of these formulas look the same. Okay, and then finally, what about r of xy? Okay, well, if you notice, these three terms already give us everything that we've seen above, so we don't need anything extra. We can just make that 0. Okay, and with those three choices of p, q, and r, we have a potential function that looks the same in all three of those lines. Okay, so f of x, y, z is going to look like x squared yz plus e to the zy plus z. Okay, so that was some work. Okay, but we have a potential function now that we can use to evaluate this integral. Okay, let's see if we can do it. Okay, so the integral along this path that we're calling C1, and remember again, that was the path that consisted of 3 line segments consecutively. All that's really important to us are the starting and the ending points. Let's maybe scroll up and remind ourselves of what those were. Okay, so 0, 0, 0, and 1, 1, 1. We're just going to substitute those in and subtract them now. Okay, and those are both being substituted into our potential function formula that we found. So we'll start by plugging 1s in for x, y, and z. That's going to give us... Okay, I probably didn't need to write all that out. You kind of get the idea here. Okay, we're just plugging x's, y's, and z's in for all of our variables. And when we plug in zeros for all of them, let's see, that first term is just going to go to 0. And the second term, actually all of them go to 0, don't they? Okay, so we get zeros everywhere. And the only question left is, what is that equal to? Well, I see a 1 plus an e plus a 1. That's going to be 2 plus e. And there's our answer. Okay, and again, we were able to do that line integral without doing any parameterization. Okay. So notice that there is a part B to this problem. Okay, let's scroll down and take a look at that. Okay, this time they're asking us to do a line integral. The vector field is actually the same as it was at the beginning of the problem, but the path is a little bit different. Okay, so C2 is the line segment directly from 0, 0, 0 to 1, 1, 1. Okay, and if you haven't already done this problem, I'd like you to pause the video for just a second here, okay, and see if you can think about how we would approach this problem maybe. Okay, so I'll give you just a minute to do that. Okay, welcome back. So let's talk about part B here. Again, we're integrating the same vector field that we were given in the problem, but we're integrating along a different path. Let's scroll up and kind of draw that path in that we're talking about. Okay, so C2 starts here at the origin and winds up at 1, 1, 1, and it's a single line segment, so it would actually look like this. Okay, what would be different about calculating that line integral compared to what we did in part A? Okay, well, I'm hoping that you came to the conclusion that it's not different at all, because the starting and the ending points are the same as they were in part A. So there's really nothing new to do here. Okay, using the fundamental theorem, we're going to get exactly the same calculation that we did before and exactly the same answer. And so this illustrates again the fact that gradient vector fields are path independent. It totally doesn't matter